Internet of Things is right now a lot of hype, a lot of raised expectations that will no doubt bring a lot of frustration. That's what happens. That's unavoidable with all new technologies. So many different things to so many different people is kind of hard to make sense. So today, we're going to try to take a one step back and apply some very simple models and syntaxes to the Internet of Things to try to understand. Maybe at first you'll think it's too simple, but sometimes you have to oversimplify things in order to make sense out of the noise that hype brings. And I will argue by the end of the presentation that the true potential of the Internet of Things is not only up to the hype, it's actually way beyond the hype. The current hype doesn't even begin to recognize the true potential of the Internet of Things. So years will have to come by, a lot of serious research and industry will have to be developed, but eventually the Internet of Things will be one of these technologies that truly changes the world as we know it. So we will start the presentation with a very, very simple syntax of IoT to understand that IoT is not just another use case of the Internet, it's a slightly new paradigm of the use of Internet. We will take a look, another simple concept, but very fundamental and constituent to the Internet of Things, is the concept of a smart object. What is a smart object? So we will have a very simple definition of what a smart object is. I will propose a succinct seven-level taxonomy of use cases in IoT. We will see that the current understanding of IoT is only level 1, maybe level 2, but there are many, many more levels we can reach. And in fact, some of them are already operational today. And after that, I will get into what is our topic of research, what is our topic of interest. We've taken upon ourselves as a research challenge the question of, can simple objects, objects that do not contain any connectivity, any processing in them, can they be connected to the Internet of Things? Because if that can be done, and we claim it can, the entire playing field changes. To connect simple objects into the Internet of Things, a key question is identifiability, the concept of identity. And I have taken the liberty to open a little parenthesis here on a very philosophical insight into what identity is, which, if you bear, I hope you'll find interesting. And finally, I will present some examples and some videos of actual research projects we've done at our group, the Ubiquitous Computing Applications Lab. Well, a simple syntax of the Internet as we know it, well, that's too simple. Well, but sometimes simplifying is a way to getting insight into things. The Internet, we can argue, is the interplay of two agents, two constituents, people and information systems. Pretty much every use case in the Internet can be represented by a sequence of such interactions. Two constituents, two agents, three potential relationships. Okay? For instance, email, okay? It's people to information systems, several hops, information systems to other information systems, eventually back to another person. Okay? E-travel, it's a person makes a request to an information system, which in turn gathers information several levels down till it collects the information from different information systems, comes back. B2B, it happens information systems to information systems. Okay? Everything is. So can the Internet of Things be represented by the simple syntax? The answer is no. No. And this is why it's something significantly different. It requires this new model. It requires a third type of constituent in the Internet, which are things, objects, physical entities that are neither people nor information systems. by going from 2 to 3 constituents, all of a sudden we double the number of relationships. We go from 3 to 6. Okay? 3 self relations and 3 relations. So the Internet of Things is any use case that involves an object. The Internet of Things as the industry and the hype represents nowadays, it's an oversimplification of that. It's basically objects with sensors that supply information to information systems. When people refer to smart cities, when people refer to smart homes, people refer to smart buildings, smart industry, that's essentially a network of sensors bringing data. Then people are only so happy to get this data, and then there's another hype, which is the big data hype on top of that one. Okay? But in this simplified model, objects are seen only as sources of data. May they be IP cameras or electricity, water, or gas meters that automatically read your consumption and transmit that, or sensors in parking spaces, or lamp posts that have all kinds of sensors in them. You know, people in the industry, people go crazy with lamps. You know, they want to put so many sensors in them. There's a term in the industry, they call them Frankenposts, you know, because they try to put so many things on them, you know, and they do they do everything except for lighting anymore, you know. But at the end, sophisticated as these Frankenposts can be, they're just a source of data. They do nothing else but that, okay? We are observing a further trend, which is the action of this underlying force in all of technology, which is convergence. Convergence is like a huge tide, you know, that changes everything through technology. You know, convergence is this strong current, you know, that all of a sudden a phone is our TV, you know, and our TV is our web browser, and everything converges because everything is the same and nobody knows what is anything anymore. So this convergence applies to this system too, and we're going to have more and more entities that are like a convergence of objects and information systems, or people and objects and people and information systems, which are maybe a hybrid, you know. It's just starting, you know, but one could argue that wearables, you know, it's a convergence of people and objects, you know. When instead of wearing these objects, they get implanted into us, this convergence will go one step further, right? What is a driverless car? Is it an information system or is it an object? Well, it is both, isn't it, right? So you could treat it as both, or you could treat it as a convergence new entity of both, okay? And will there ever be a triple convergence of information systems, objects, and people? Well, sure, all the military research is seriously thinking about that. You know, the soldier of the future is probably a triple convergence of these three things, you know? And eventually, hopefully, as things usually go, this military research will eventually make it into civil use, you know, and we will have, I don't know, super workers or people with exoskeletons and information systems and things like that. Something to watch out for. So far, most use cases can well be explained without this convergence, but I thought it was interesting. Just warning. So objects are these new constituents, the new constituent that makes a difference, that makes the Internet of Things something different from the Internet as we know and love. And what is a smart object? Well, a smart object it's in fact a very simple notion. Is the recognizing that any object worth any interest, it's made of two parts. One is its physical part, its atoms, its matter. But then there's an information part to it, at least information. Even a simple product will have a brand, will have a price, will have a expiration date, important information, without which it cannot be consumed, it cannot be sold, it cannot be used. Okay? On another end of the spectrum, a telephone is nothing without its firmware. Okay? All objects have a digital and a part made of bits and a physical part made of atoms. And it's the looking at the object as both of them is basically a way of thinking of objects as smart objects. Also, objects interact bidirectionally with its environment, both through its physical and digital part, inputs and outputs, sensors and actuators. Okay? Let's see a couple of examples. Well, first, IoT in its simplified way, it's a smart object that basically senses and supplies data. Okay? Just the IoT, if you go to an IoT conference nowadays, it's university here, our obligation is to look beyond. Okay, a driverless car is the textbook example of a smart object that has everything, has digital part, has physical part, has many sensors, has obvious actuators, and it sends information in both directions. Okay? But if we were limited to examples such as a smart car in which everything is on the physical location where the object is, we would be limiting ourselves a lot. Things become interesting when the digital part can be placed in the cloud. And then all of a sudden, objects that are cheaper, simpler, can still be smart, even very smart objects. An example is the Alexa, Echo, or these devices, which you can talk to, okay? And they can respond to you, and they can actuate on your home. They can open the door, they can change the lights, they can play music on your stereo. But the processing, most of the intelligence, most of the digital part in this case, is in the cloud. It's not in the physical object. And when we realize this is possible, all of a sudden, say, well, then can we make even simpler objects smart objects? Yes. For instance, a suitcase. Let's imagine a suitcase. We want to make it smart, so it arrives at the destination when we arrive, instead of being lost. A smart suitcase would be a suitcase that can ask questions, can physically actuate on the conveyor belts and classification, and it's a suitcase that could drive itself to destination, route itself to destination. Do we need to put a processor on the suitcase? So the research question, the key question is, what is the minimum? What is the minimum technology? What is the minimum sensors that the simple object such as a suitcase must have in order to assign itself an intelligence on the cloud, pair both of them, and convert the luggage into a smart object? Well, as it turns, as we will see later, all we need is for the suitcase to generate which, where, when events. That's a minimum. If we find a way of a simple object to generate these events, this identity and location in time-space coordinates, these events are enough, for its digital intelligence, which can be in the cloud, to take over from there. Okay? That's a minimum we need. And as we will see, that's not very hard to get. So, smart object, the central idea, a smart object does not need to have the intelligence on board. Okay? And technology, cloud technology, wireless networks technology has made this possible. Okay, so in IoT, I've defined taxonomy of 7 levels of cases for a smart object to do in increasing complexity. First level is smart object is an object that senses and supplies data. That is, as I said, as I claimed before, that is where most people understand IoT to be. Maybe level 2 is they go a little beyond data and they do some interpretation in the data and create events. For instance, some of the lampposts will have microphones and cameras and will provide the video and audio stream. But there are some that are a little more intelligent and are able to, with local processing, determine whether a certain noise has been a gunshot. Okay? So the street lamp is able to send an event to the police station. There's been a gunshot in my vicinity. Okay? That's going beyond data into an event, just as an example. Well, but smart objects can ask questions, can retrieve information. That's another level. With this information, they could make predictions, which to some people, the ability to predict is the core of intelligence, right? To predict. With these predictions, they may take actions. The next level is these actions are oriented towards fulfilling goals. And the last level is they don't only take action and fulfill goals, but do so as part of a team. And in this team, there can be other objects, people, or information systems. Okay? Well, so it'll take centuries to get to level 7. No, we have examples already of level 7 smart objects. Let me show you one. It's not even very expensive. Okay? Thermostat. And sometimes when we make these taxonomies, we think, well, it's got to be something very complicated. Well, a driverless car fits the level 7 too, right? The car and you have the common goal of going somewhere, right? Safely. Well, a thermostat. Well, Nest thermostat is a thermostat that, of course, can sense the temperature, but it turns this temperature into events, too hot, too cold, interprets the data at a very simple level, but it also retrieves information, retrieves a lot of information about weather predictions, about the location of the people in the house. So it's able to retrieve this information, but with this information, it makes predictions. It predicts future weather, future occupancy of the house, okay? And with these predictions, it actuates on the heating, ventilation, and air conditioning system, okay? It does not only say it's too hot, turn it on, turn it off. It's too cold, turn it on. No. It makes predictions based on the weather, based on the location, based on pattern analysis of over the days and months and weeks of the behavior of the occupants of the house, okay? And tries even seasonal variations, and it tries to make a prediction of what is the optimum level. That is fairly sophisticated, by the way. All this is done in the cloud. So in doing so, it fulfills a goal. It's a double goal. It's keeping a comfortable temperature, also minimizing the energy consumption. That's just an important goal, right? And in fulfilling that goal, they cooperate with humans because humans can go and change the thing. So it's not only you don't give full control to the thermostat. The people in the home, they reserve the right to make changes. So it's a cooperative. And when there's a human override of the temperature, the Nest sensor will take that into account into future predictions, as in any member of a team would do. Learn from the behavior of the other team members. So, well, that's level 7. It's just a thermostat. So, is it a big deal? Well, I think it's a big deal. I think it's a big deal, and so did Google. When only 3 years after founding the company, after the foundation of the company, Google bought it for $3.2 billion. It's a lot of money. Okay? It's a lot of money. I could argue a single device with this level of intelligence could do more for climate change than most of the public policies of the United States. That by saving money back in the taxpayer's pocket, more than most of Trump's tax cuts. So here with IoT, we're not only doing simple use cases, we're out to save the planet and the economy at the same time, right? It has a potential huge impact. Only a thermostat, only an intelligent thermostat. There's so much energy and all the consequences, economic and environmental, of saving energy. So, and this is a potential opportunity, okay? Actually. Well, now we go into the topic of can we connect simple objects? Of what is a simple object? Well, let's define a simple object as an object with no digital part per se. Okay? A book, shirt, pair of pants, pair of glasses. If simple objects are out of the IoT paradigm, then IoT loses a lot of interest because most objects we interact with are simple objects. I mean, if IoT were only about power meters, parking spaces, and lamps, it'd be interesting, but it would not be life-changing for most people, okay? Would not be. Now, if objects we interact with all the time, objects are things we eat, things we wear, things that make us smarter because we learn through them, you know? If these simple objects can be connected, then something changes. Well, the answer is yes. In order to connect a simple object to the internet, we need two things. First, certain technology, whatever it may be, that can detect which, and I'm not saying what, I'm saying which specifically be two objects that are alike, they are the same answer to the what question. No, the question is which. Exactly which object, true item identity, which, where, when. So it's identifying an object in time and space with a maximum possible prediction. If we have a technology that can generate these events, then we can connect the simple object with a piece of software that is and goal-oriented, and for those of you who have been in computer science, you know, software that is autonomous and goal-oriented is customarily referred to as an agent, software agent, that becomes the digital alter ego of the simple object. And that software agent, weakly but significantly connected to the simple object, they both can form a smart object in its own right. Okay, and that is, we found, a very interesting topic of research, you know, because smart driverless cars are interesting, but when it's going to the critical, to the simplest possible form of a simple object. So the mere presence of an object in a space-time coordinate is a meaningful enough event for many IoT use cases. Also, and we've done research on that, if we can detect the event of an object being interacted with by a human, that's a different kind of event from the which, where, when, and which is very significant. If we can detect those events, and we've put some research effort into that, this can trigger also a lot of IoT use cases. Let me open a philosophical parenthesis here, because I took the liberty, I hope, please bear with me with this philosophical insight about identity. Identifying the object is key. So start thinking, what is identity? What is it? Well, it's obvious, you know. You are you, and I am I, and he is he, you know. But when you go to objects, you know, what makes two objects different? Two shirts of the same size, same color, why are they different? Well, they are different. You know? But when you keep going down, 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 is identity always there? Not really. Not really. If you go down all the way, to elemental particles, they have no identity. Two electrons are not different from each other. And this is a physical statement, at least to the best of physical knowledge nowadays. Elemental particles are indistinguishable. Indistinguishable, meaning that if two electrons are swapped, there is not a new state of the universe. In fact, Fermi, Dirac, Bose, Einstein statistics are based on this fact. Okay? Well, an atom they don't have an identity either. Molecules, they don't have identities. So where does identity emerge? Identity emerges when enough molecules pile up, so there starts, so certain randomness starts appearing. And it's in the randomness of macroscopic levels, in the random variations of many, many things coming together, then all of a sudden, identity appears. And this is intrinsic identity. Okay? And I want to distinguish between intrinsic identity and assigned identity. Most of the time, not always, but most of the time, we are not able to recognize through technology intrinsic identity, so we assign an IP is an assigned to computers. Okay? We humans, we recognize each other through intrinsic identity. We don't need name tags. Okay? But still a little more interesting, two eggs, from the same hen and fertilized, they are basically, essentially, single cells. So they are from the same hen. They are identical down to the same DNA, right? But they are different. And the difference is only in the randomness. If you take a very close-up view of the shell, one egg and the other egg, they will be different. And that would be an intrinsic identity that could be used to identify. But it's in this randomness that an identity emerges. Interestingly enough, I think it's an interesting insight, identity has its origin, I argue, in the randomness at microscopic level. It's the same origin as the concept of past and future, the concept we know as the arrow of time. At the microscopic level, most physical models argue that there is no such concept as future and past. Time can go in both directions. For instance, in this video, which is what millennials would call a boomerang, it's a video that goes back and forth. Everybody knows which is forward in time, which is now, and now it's backward in time. Well, from a physical point of view, both are possible forward in time. What makes us all so sure that one is one is going forward and one is going backward? It's just a question of randomness and probability only. There are so many more orders of magnitude of unmixed states and so many fewer orders of magnitudes of unmixed states that going from unmixed to mixed is highly probable, going backwards is highly improbable, but not impossible. So the concept of past and future is just a question of probabilities and entropy. If any of you is familiar with Feynman diagrams, it is interesting that at the microscopic level, there is neither identity nor direction of time. And it's an accepted principle or model in physics that, for instance, antiparticles such as positrons are nothing but electrons traveling backward in time. And nobody has a problem with that. Recognizing that the direction of time is just a question of probability at the microscopic level. Okay? So I thought it was an interesting insight I wanted to share with you, that identity and direction of time emerge, from the random microscopic systems. Going back to reality and the engineering point of view, well, can we use that intrinsic identity, now that we have a firm understanding of what it is, in order to identify the three constituents of the Internet of Things, namely people, information systems and objects? Well, with people, yes. It's only very recently that this has become mainstream. Very recently. It's how many years since we can clear customs with biometric levels? Not many. How many years since we can log onto our online banking account with our fingertip on our phone? Not many. But now it's mainstream, right? And this is very different. We finally are using intrinsic identity, which is our thumbprint, our biometric measures, instead of a signed identity, which is a weak kind of authentication, because a signed identity can be transferred, can be duplicated, while intrinsic identity, it's safe. Safe. It's not easy because you have to find randomness, but permanent randomness. Yeah? You have to find intrinsic identity for authentication has to be based on a randomness that is permanent, that doesn't change with time. For instance, body weight wouldn't be a very good way. It's randomness, but it's not permanent, right? Now the question is, can we do the same for information systems? Because information systems, we use a signed identity, either through IPs or digital certificates. Well, there happens to be a technology that uses randomness. It's called physical unclonable functions, okay, which is it's a clever way of using the random variations in the delay of logic gates, which is a physical, intrinsic, permanent randomness in digital circuits, that you can build a circuit that once you build it, you can extract its identity through a set of challenge responses, which are unpredictable, but they are permanent. So once you create that one, you can identify it, and forever after that, keep identifying. And that is based on intrinsic randomness of the silicon. Why is this not used more? Beats me. I don't know. If I were security, I'd be putting these chips everywhere. It must not be expensive. I don't have an answer why not everybody is using this. Now the question is, and can we use intrinsic identity to detect objects? Why isn't there a discipline of object metrics, like biometrics for objects? Well, with the resolution of cameras and the cost of high-resolution cameras, it would be possible. And I think it's a worthwhile topic of research for whomever wants to take it up. I think it's a very promising. It's a blue ocean research. You won't have much competition, and you will have industry knocking at your door. If you can come up with a cost-effective solution of identifying objects, even a niche class of objects, if your solution only works for a niche class of objects, through some inexpensive technology, whatever, ultrasounds or high-resolution cameras or some kind of laser reflection of something, that would be worthwhile research and definitely applicable. So object metrics, if you want to take it up, I would encourage you. I think it's there are very few, to my knowledge, there are very few efforts in that sense. In the meantime, for objects, we use a signed identity. And since we want to identify individual items, not classes of items, barcodes are not enough, so we either use QR codes, which are used quite extensively, or this technology, which is well known, so I won't present it, which is Rfid. Rfid is a unique license plate for every object, which can be interrogated and retrieved through radio waves. So it can be in many objects at the same time, even when objects are not visible to the eye. Through Rfid, identify objects uniquely. Now, this is a technology that will allow us to generate these which, where, when events for simple objects and connect them to the Internet of Things. And this is where our research lies. Okay? There's a lot of things you can. So we started with a test bed, and we made two kinds of smart objects. One is both simple, shelves and books. Yeah? shelves and books. Okay? The shelf itself is a smart object, okay? Because you can ask questions to the shelf, such as, what books do you have in a certain position? Yeah? So we have people, information systems, books, and shelves, and that was our testbed for a little while to do certain. So we sensorize the shelf, we put antennas on its back, we assigned radio frequency identities to every book. So all of a sudden, we could find out at every instant of time where, with a certain resolution, the book is. So we change one book from the top to the bottom of the shelf, that is a different event. So we can detect these kind of events. What can you do with that? Okay. One of the first applications was to shopping for people with handicap, with mobility impaired people. People bound to wheelchairs, they can do pretty much everything in life. They cannot go shopping by themselves for the simple reason they cannot get up and get things and browse things on shelves, right? So they have intimacy limitations. They have, okay, can we use these simple object IoT use cases to help them? Okay, so now if the person on the wheelchair has a handheld device, we also added augmented reality through some QR codes. We could project. We found a way of translating every pixel on the screen to a physical location on the shelf, so the person on the wheelchair, by just clicking on the screen, can ask the question of the shelf. So it's the person is asking the object shelf, what do you have in this position? So the shelf is asking the other objects, which are the books. Books, can you identify yourselves, books in this position? You know? So the books answer the shelf answers the person. Actually, in the meantime, the shelf gathers more information about the books, such as author, ISBN number from a database, takes all that information and presents it to the final user. See how that works in the syntax? No? People, objects, information systems. Yeah? People asks object, objects ask other object, these objects responds, object asks information system, collects the presence information with additional bibliographic information about the books, and responds to human. Okay? It's a fairly complex IoT, way beyond already. Okay? Of course, we can also, rather than using a handheld device, we tried using the same thing, but on a on-head display, similar to Google Glasses. In this case, it was a different brand. Okay, but basically, in this, rather than clicking on the screen, it was focusing the gaze on a certain point is equivalent of clicking on the screen. Okay, just dwelling for when the gaze was dwelled for a second or more in a certain position, it triggered the. There's a paper published on this, and Rfid got his PhD thanks to this research. He's in Imperial College in London, continuing research on wearables for healthcare. Okay. Also, with the same shelf and the same books, we tackled the problem of detecting the interaction of a human picking up a book. That sounds like a simple problem, but it's actually a very complicated problem, because okay, when you pick up a book, the shelf will no longer detect the book, so that takes too long. By the ceases to detect the book, that's been many seconds, and the reaction time is not good enough for any practical purposes. So what we needed to do is to analyze, all the RFID variables, power, phase, which are not static, are fluctuating through environmental changes, and out of this fluctuation, detect significant enough fluctuations without generating too many false positives, in order to effectively detect and through some weighted information gain algorithms, we were able, with fairly good metrics in terms of minimizing false positive and maximizing accuracy, detecting this. This is significant research in the sense that the moment you can reliably, and we don't claim we have solved the problem. We have made significant progress, but we haven't solved the problem. It's fairly reliable, probably not reliable enough. But the moment you solve that problem of reliably detecting interactions, you are creating an event in physical space that is akin, that is equivalent to clicking on virtual space. And clicks are a very significant event that trigger a whole economy based on clickstream analysis. If you can mirror that in the physical world, we coined the term crick. You know, the physical world sometimes, as opposed to the virtual world, is referred to as brick and mortar. So we call the click in brick and mortar, we coined the term crick. So crick is a physical interaction, but if you're physically interacting with a physical object, which happens to be a smart object, you can create very interesting use cases. Okay? And you can do clickstream analysis, which is the analysis of interactions in physical spaces. There was another paper published about this research. And we realized that sensorizing shells was very limiting because it was very expensive. You know, if our solution to connecting simple objects to the internet is going to be based on putting antennas everywhere, that's going to be very limiting. So we opened a new line of research, which is using a robot, which is, if you cannot put antennas everywhere, have a way of moving the antennas around the space, you know, as a cheap alternative. It's not as good because it's not as real time, but it's possible and it's feasible. Okay, so we did the next test bed is the books again, also garments and a robot. So there was the development of an inventory robot, a robot that can detect the presence of objects in a space. Okay, and that has ever since transferred to industry, and it's being commercialized, not very successful yet, but there is a lot of interest. And it's basically a robot that can go around. In detecting the presence of objects, we were tremendously successful. There is no technology that can inventory a space full of objects more accurately than this robot, none. And that brings metrology problems. If you have the most accurate tool for something, it's very hard to measure its own accuracy. Okay? But the problem that's still open, and Mark is working hard on that, and it's about to finish, is going to be the problem of, by the way, the development of this robot was published in an Elsevier, in a Springer book on ROS, Robot Operating System. And I was forgetting, yeah. And we did a derivative on this, is once we could find the presence and estimate the location of products in a store, we could create a virtual visit of the store. The idea was, you're all familiar with, right? Well, you could go in the store and try to find out what's on the shelves, and the information you would get would be freshly gathered information by a robot. Okay? So you would go into the store and be able to interact with the shelves of the store and have information that might not be up to date, but might be less than 24 hours old. Okay? Which is of great interest. When we did that, we realized the accuracy on which we were estimating location was not good enough. Okay? It's not good enough. The robot detects products very far away and detects it many times, so there was a high uncertainty. So the next problem we tackled was, can we, from all the information of all the different reads of a certain object by the robot in many different locations, can we infer its position? Okay? Well, this is the paper on the street view like visit to the store. Oh, sorry, I'm going to the wrong order. We will visit the location problem later. But we opened a second branch of research, which was the robot worked well, but the robot is especially useful. The robot is especially useful for very, very, very big surfaces, huge stores, you know. And at this point, more than one robot may be necessary because one robot doesn't have time to invent everything. So more than two robots, more than one robot, 2, 3, maybe more. And it just makes sense that these robots cooperate, right? So these robots do their own planning, they have to cooperate. Things were very, very complicated. At this point, we did something which I think was smart, which is let's stop and let's turn 180 degrees. Let's go the simple way. Rather than include very complex planning algorithms and very complex cooperation algorithms, let's find a way to cooperate without any planning and with very simple algorithms. And for that, you look at concepts such as swarm intelligence and stigmergy. Stigmergy is using changes in the environment to communicate with each other. It's what the ants do in their goal of bringing food to the nest. Okay? So we define a very simple robot that doesn't even plan its route. It basically has sensors for objects in 4 different directions. It has an algorithm so that it won't crash, and it will follow the direction where more new undetected objects are found. Okay? And as it detects these objects disappear from the sensors of the other robots. So as the robot is detecting, it's sort of flagging the objects as already known, and is effectively changing the environment for the other robots, which will not be interested in going to where this robot has been. So it's an extremely simple way of cooperation. That's essentially what ants do with pheromones, right? So a robot will take 4 quadrants and pick one and go in that direction as long as it doesn't crash. You know, if it's going to crash, it takes another direction, and if there is no preferred direction, it will pick one randomly. In simulation, it worked beautifully. Okay, worked beautifully. This is a robot that is going around without any map, doesn't even know where it is, doesn't need to. The same way that an ant doesn't have a map of its environment. Okay, it just has a very simple local planning algorithm not to crash, you know, and it follows the smell of new objects. Okay. It can be mathematically demonstrated that in bounded space, you know, this simple algorithm will detect everything. Yeah? It's not possible to put a maximum cap on the amount of time, but we know it will finish. And only very recently we've started to do tests with actual robots, okay, in the library, which are very nice to us, you know, and and let us do this. We do these tests even with students there, you know. They seem to trust our robots that they won't crash against anybody. But these 2 robots are just let go anywhere in the. They don't need to know where they are. You don't need to map the store. You don't need to map the library in this case. And the 2 robots will go each one their own way. It looks like they're cooperating, you know, because when one goes this way, the other one seems to go a different way. You know, they don't try to compete. They do cooperate, and and this is all very recent. This just happened in the last weeks. You know, the initial estimates is that the accuracy is very high, and we believe this is revolutionary research in the industry. Nobody in the robot business is working on this in this line of research. And finally, the location problem, just to finish my talk today. The location problem is very hard, yet it's very valuable. industry keeps telling us, if you can tell us where objects is, this is so much value for us. I could go on and on why, but just take my word for it for now. The location is extremely valuable information, yet it's complicated. So the problem with a robot and location is that the robot detects things so very far away. For instance, an object in the center, it will be detected from this side, from the other side, from the other side. So you have a lot of information, so you cannot use the position of the robot to estimate. So what we do is we create a detection model. We started trying a geometric detection model, so like a pyramid shape of the beam of the antennas, then an analytic detection model, which is the pattern of the antennas, but at the end what works is a calibrated detection model. You take many measures of tags and you have an expectation of what parameters you will receive from a tag, from an object, RFID tag in a certain position, okay? That is what the detection model is, an expectation of what an object in a certain position will be, with what parameters it will be detected. Then these are what you detect. The EPC is the unique identifier, the timestamp. The RSSI is a power measurement. It's a relative signal strength indicator. Phase, frequency. At the end, it's finally the power. That's the factor that it's more useful. Phase, we will keep working and see if we can use phase, but for now, we get most out of, and the position and orientation of the robot. So you create a prior, which is, a prior is basically a distribution of probabilities of the location of a certain tag in space. Initially, all you know, it's got to be in some shelf. A book cannot be hanging in the middle of the air between two shelves. It's going to be, so you divide space into bins, in our case with 30 centimeter resolution, 30 centimeter wavelength, okay? And you equally distribute the probability about all positions on the shelf, okay? Then you're going to have many reads of the same tag, okay? And you keep processing iteratively, okay? You use bias filtering and say, okay, given this detection, what is the posterior probability distribution of the tag, and that reduces focuses the probability on a certain location. And now another read from another port, it will focus more, and you get, at the end, your estimated location is the space bin with highest likelihood. And this is our results, which are frankly good. X, Y, Z results, these are very recent, This is basically saying that the median error is way below half a meter. And it's that's good. Actually, I would say if this can be translated into real life industrial applications, it's actually very good. Okay. It is true that there are lots of outliers here. There will be objects that are read only once from far away and its position won't be accurately. But in our interactions with industry, we've been assured that even if we get 80% of the objects with good enough location, that's plenty, compared to what they have now, which is essentially nothing. Okay, so and this is my last slide. What comes next? Well, what we can accurately detect the presence and location of any simple object. And we can reliably detect person-object interactions, and these are the two main topics of our research right now. Simple objects, not only driverless car and Amazon Echoes, but also simple objects, will be able to turn into level 7 smart objects. We can imagine food products cooperating with you to prevent allergenic attacks. You pick up a yogurt, and the yogurt can warn you, hey, I'm not for you. I have nuts, and you're allergic to nuts. See, this is an object predicting, taking action, cooperating. Products which can advertise themselves individually to you. Because if products well, actually the digital alter ego, the software agent of the product, knows where the product is and can ask questions and know where you are, you can know it, you happen to be in the vicinity of the object. You can advertise directly. Okay? This is not one-to-one advertising. This is not one brand to one person advertising, which is already very advertising. This is one object, particular object to one brand. And this advertisement will only happen if the boots are your size. If not, it won't happen. Okay? Products will manage their own life cycles from manufacturing to recycling. It's very important. Battery can be made responsible for its own maintenance and its own proper disposal. And I think it's very important for logistics. Packages will be responsible for their own routing. Why is Internet so powerful? Internet is a simple concept of information packages with addresses that go to routers and with very simple algorithms get dispatched. Well, with this idea of smart, simple objects, logistics could be the same. Logistics are now governed by central planners, which are very inefficient. If you could give the responsibility of its own routing to every package, the logistics would happen like the internet. Distribution centers would be just like switches or routers, right? Package arrives, and it directs, given its address and its destination, it directs conveyor belts and classification systems, jump to another truck, to another distribution centers, to the home. Okay? So a package, and I can bet that Amazon will be using this kind of technology soon, because the exponential growth of point-to-point shipments, is calling for the use of simple objects, the conversion of simple objects into smart objects in logistics. These are just 4 examples, but with this simple syntax of the Internet of Things, with this 7-level taxonomy, I'm sure you can imagine a lot more other use cases, and I encourage you to do so and to maybe do some research on it. Thank you very much. Yes. You're going to get a microphone now.
Thank you for your presentation. Could you tell us about the risks or the dangers of IoT? Because, for example, imagine that the thermostat that you have described, you have said that it registers the times in which there are people or not in the house and predicts. Imagine that a hacker gets this information and realizes that on Friday night the family goes to dinner out, and well, the thief knows that they can go to the house.
Yeah.
Could you explain us about this or other risks?
This is definitely a risk, but I don't think it's fair to pin this risk on the IoT. This information exists already, and it's because your phone has a GPS, and it's collecting data, and it's there already. It's whether a thermostat uses or not, that information is there. See, so the IoT has risks. Those privacy risks, I don't think they are inherent to IoT. The risk of IoT is that you have all of a sudden, you have a lot more of entry points for hackers, so the vulnerability of the network increases. And this is true. This is why I was so adamant about intrinsic authentication of systems. For instance, there was a case very recently in which hackers got into IP cameras. They could change their firmware, and they had, I don't know if millions, but thousands and thousands of IP cameras perpetrating denial of service attacks on computers. That is a risk of IoT. Some people, and I've been in a meeting with Microsoft people, and they say, well, in order to prevent that, we will define IoT, in IoT, devices will only be clients. They will now, by cutting the capabilities of IoT, that's one possibility. So make cameras more secure. Do a little research. How can you make a camera not vulnerable? So assigning a digital certificate to every IP camera or power meter or parking meter is possible. I think there has to be a simpler solution, and I think unclonable functions, are a better option. But there are risks, and the risk is basically linked to the explosion of vulnerability points in which you can, and that they are not going to be as secure. And since they are connected to the network all of a sudden is a lot more vulnerable. And this is a serious issue with the Internet of Things, and I think until this issue is resolved, this will prevent IoT from widespread usage, because a lot of people are scared. You had a question. Angel here.
Yeah, I was going to ask about security too, and you already covered that. But let me ask another question. So you talked about the fact that devices can have their intelligence resident or in the cloud. Which one do you think is going to be prevalent? Because a device that has its intelligence in the cloud is dependent on its connectivity, right? So when it's not connected, it's blind. Actually, it's not smart anymore, right? Whereas a device that has its intelligence resident is more complex, it's going to consume more power, right? So which of the two paradigms you think is going to dominate the market?
I think it's going to be in the cloud. Well, if it's by numbers, more smart objects will have intelligence in the cloud. Of course, objects that can have the processing on board, such as cars, will have them on board. Although what part of a driverless car intelligence will be in the cloud, I think it's still for debate, probably a lot. No, the point here that I try to make is that you don't need continuous connectivity between the physical object and the cloud. The agent representing the object can keep acting and only needs the minimum connectivity is that the digital alter ego receives a few events. And these events can be few and far between. For as long as an object doesn't change its position, the digital alter ego can keep going and doing things. Doesn't need to be in connection. No? Only when there's a change of position or an interaction, you need to detect that event, and at that point, as soon as related. So you don't actually need permanent connectivity between the two. Only when an event that is significant for the goal and decision making of the digital intelligence in the cloud happens. And most of the time, in many simple objects, this doesn't happen very often. Okay? For instance, an object might be a refrigerator that's cooperating with the family, so the family eats a healthy diet within their budget. Okay? Does the refrigerator need to be connected all the time? Not necessarily. The refrigerator only when there's a new product go in, or a product can go, and how many times does that happen? Maybe 10, maybe 100 times a day. That's it. Only those events which are significant, which change the state of things, need to be transferred. Is the which, where, when events or interaction creaks events. And those are not very often, and they don't need a lot of, and the kind of communication that you need for this is a very low bandwidth communication, which falls into what we call M2M, no machine to machine kind of thing. Very low bandwidth that you can use many different. So it's more the M2M. So it's not even competing with a regular internet. Did I answer your question?
But then these objects are not really smart, right? Because smartness
Well,
is in the cloud. So
yeah, but it's how you think about it. And is your intelligence, the intelligence of the edge or is the cloud? The fact that they are not physically co-located doesn't mean that a software engine doesn't form part of the physical object. So it's a change in how you approach it. If you have a software, which is an agent, that is autonomous, that is working only on behalf of a physical object, I think you can argue that it's part of that object. Because it's a software that is only acting for that. So if it's a general software that's working for everything else, then you're right. Okay? But if it's a software agent, that's a digital alter ego, and it's working only to fulfill those goals of this, then you could argue that. Okay?
Any other question?
You have talked about this, the last part of your talk. It was very nice. So I understood that by using the received power value, you try to predict the location of this object in the environment or in the shop or library. So I also working on something similar. So I have one question. You said this RFID has some limitations. So my question is, you try to use several robots at the same time to somehow increase the diversity of this measurement. So could you use several antenna or array of antenna instead of having several robots in this environment?
Yes.
I mean,
yes.
so I think this is even cheaper or much simpler.
No. Yeah. There's an alternative to a robot going around, which is placing antennas, for instance, all over the ceiling. In the algorithm developed in this case would apply to, okay? Would apply to, instead of having mobile antennas, having antennas spread out in the space, reading tags from. The robot is more accurate. The robot is more accurate because it gets closer to the antennas. It has a lot more diverse positions than antennas. But yes, you could have the different antennas located. And it's a solution that has been tried, not very successfully yet, but it is an alternative.
Okay, I have a couple of questions. One is already, security part was already the first one. And actually, on that line, just to reply to your answer, or that's my point of view, I would say that also there is this, you mentioned this where, which, and
When.
And that's the kind of the fundamental question, that's minimum information that you really need to. But I would add that also some other information for the security part would be good to have, because otherwise examples as the Mirai attack that you already mentioned, that attack, that DDoS attack happened. So I would say that's something that cannot live on a different layer, but something that should be. That's my point of view. I don't know if.
No. I think you can never. You cannot overestimate the importance of security in IoT. And if we do that, we'll kill the entire business. It's not our topic of research. It's not what we spend research time on. That does not mean we don't recognize the importance. This is what I went into this philosophical disquisition on identity, because it's extremely important, and we hope on the security experts to bring enough security layers so IoT flourishes into all its potential, because security could kill IoT. If it's the easy way out to security, just not do it, And if people become afraid, if there are incidents of attacks through IoT infrastructures, it will finish killing the business. Yes.
I'm afraid it could be. And the second one is just to ask you, what do you think about blockchain? That's the other hype. So we have one hype, which is Internet of Things.
Well-
We have another hype, which is blockchain, and it looks like it's
Yeah.
they are
If
gonna
the
be
Internet
together.
of Things, on the other hand, does flourish, big data will be small. We'll have to find a new word. The amount of data will be way, way beyond what we even refer to now as big data. And there are active lines of research, even in the industry, of using blockchain and infrastructure
I know, I remember that.
for a ledger. There's
IOTA.
IOTAs, which is
IOTA.
even a digital currency, similar but different to Bitcoin, to pay for IoT-based services. So blockchain and IoT, it's a very promising line of research too. And I know for a fact that at least Microsoft has a line of work on that. Everybody has, and every big name, be it Google, be it Amazon, be it Microsoft, they all have big IoT departments. And at the very least, Microsoft is already in Azure. Azure is the big cloud infrastructure of Microsoft. As far as I know, they already have a blockchain component, and one of the main justifications of having a blockchain component in Azure is the IoT applications.
Okay, thank you. No more questions? Okay, so let's thank Rafa again for the talk.